So, I would like to go over some topics for the next two sections on 13.4 and 13.5. And then I will go over 13.4's again, and then I will also go over 13.5 and do some examples. But this is just to give you an idea what the two sections are covering. So one of the topics that we will cover in 13.4 is the unit tangent vector, and we use the notation capital T, bold capital T, for unit tangent vector. The unit means that the length or the magnitude of the vector is 1. Tangent vector is a vector that is going to touch the curve at one point. Then there is the normal, N, capital N, for the principal unit normal vector. Then we are going to cover the binormal vector. And all three vectors that I just talked about are all unit vectors. That means the magnitude or the length is 1. Then we talk about acceleration, which is also a vector. We talk about curvature and torsion. Curvature and torsion are scalars. So they're just going to produce a number. Curvature is not going to be 0 or is not going to be negative. However, torsion could be 0, negative, or positive. So we are going to start with let RT be a vector function. Let S be the parameterized arc length. We covered this in the previous sections, how to parameterize a curve and find arc length. And let P be a point on the smooth curve of the vector function RT. So for instance, I have a couple of graphs. This is one graph, is a graph of a circle. So let RT produce this circle. And then we want to talk about these ideas. What is the unit tangent vector here, normal, the principal unit normal vector, the binormal vector, and so forth. So the tangent vector is going to be tangent to the graph. Its length is 1. And what it does tell us, it points in the direction where this point is traveling, or this point, or this point. So that's what the unit tangent vector does. It points in the direction where we are traveling, or that point is moving. The other idea is the principal unit normal vector. But before I talk about this one, let me talk about the curvature. The curvature is the magnitude, so it's just a scalar, is a number, that is a magnitude of the change of the tangent vector with respect to r length. That means how much this is changing, how much the tangent vector is changing when the object is moving on this smooth curve. As you see, this is just constantly has the same change, and so forth. So that is what the curvature is. And a curvature also has a formula, and we use the letter kappa. This is called kappa, looks like K. And kappa is equal to 1 over r for a given point. So if the curve that we have is a curve of a circle, is a complete circle, because I wanted to put a circle, it looks like an oval, but this is a circle, then the curvature for this one is just going to be constantly the same value. But if I want to find a curvature, let's say if I have a path that looks like this and I want to find a curvature for this path, at this point, the curvature is going to be smaller. But if I go here, if this is if I'm going this way and then this way, this is the direction of the curve, then the curvature here, because the change of the tangent line is not very strong, it almost has the same direction, then the curvature here is going to be small, but the circle that hugs this point is going to be very big. To measure the curvature, we are going to measure the circle that is going to be tangent to the point to measure how fast the tangent vector is changing. And the bigger the circle is to hug that length, the smaller the curvature is. Another way of thinking of a curvature is, imagine you are on a very tiny roundabout that has a radius of 10 feet, and you are going around this roundabout. You have to change your wheel very rapidly. So you're driving on a roundabout that has a 10 feet radius. So you constantly have to twist your wheel to be able to go around the roundabout, almost to the point that you can't twist the wheel of the car any longer. But if you have a larger roundabout, let's say its radius is 100 feet, then you are not going to make that sharp of the turning your wheel to go around this roundabout. So the bigger the circle is, the less you are going to turn your wheel, the smaller the curvature. If the roundabout has a very small radius, you have to constantly turn the wheel very sharply. So the circle is smaller, the curvature is bigger. And if you have a windy road that you're going on, then the curvature is going to constantly change, because when there is a sharp turn, the curvature gets bigger. If there is not much of change, or there's going to be like a straight and then a sharp turn where you're going straight, then the curvature is super small, because the circle that is tangent to that arc length is going to have a bigger radius. So they have an inverse relationship between curvature and the radius of a circle. The bigger the radius is, the smaller the curvature. The smaller the radius is, the bigger the curvature. And I will demonstrate an example. So the next thing I wanted to talk about, now that I talked about the curvature, is the principal unit normal vector. And the curvature tells how much the path is curving. So that's what the curvature does. It tells us how much the path is curving. However, the principal unit normal vector n tells in which direction is curving. And this normal, this principal unit normal vector is always pointing to the center of the circle of the curvature. So right now this is pointing to the center, this one is also pointing to the center, and this one is pointing to the center. So the green vectors are the principal unit normal vector. The principal unit normal vector is perpendicular to the tangent vector, and that's what it does. It always points to the center of the circle of this curvature for that point, and is perpendicular to the tangent vector, and both of them have a length of 1. And these two, T and N, together going to form a plane. So the cross product of T and N is going to produce this vector, binormal vector. And binormal vector is perpendicular to the plane that T and N create. So T and N are on the plane that is called oscillating plane. So right now the oscillating plane is on this circle here. Then I have it right now here, is not changing. This is the other one. So these are between T and N. We have a plane, and that plane is called the oscillating plane. Then I mentioned binormal very briefly right now. The binormal vector is perpendicular to both T and N. And to find B, we just take the cross product of tangent, unit tangent vector, and the principal unit normal vector. So the cross product of those two give us another vector perpendicular to both of them, which is called the binormal vector. We could find the acceleration vector by adding T and N, which I will explain it to you on the next section. And then we have another thing that is called the torsion. And what the torsion explains is how much this oscillating plane that is made here is twisting. If I have a 2D graph of a circle, this oscillating plane is always going to be on the circle and is not going to twist. So torsion, which we use the letter tau, is going to be 0. There is no twisting to the oscillating plane. When this oscillating plane twists and turns, that is when binormal vector also is going to twist and turn. So if there was a curve here, if it was a 3D and I had a curve here on the ground, then this binormal vector perhaps would look like this. This is N, this is T, this is our binormal. And if it's on top here, that is tangent, this is normal, and this would be our binormal, maybe like that. So this is the binormal is twisting and turning, so is the plane is twisting and turning. And to measure how much this is twisting or turning, this plane or the binormal vector, that measurement, that magnitude is called the torsion, which we use the letter tau. So I have graphed, supposedly this is a 3D graph of a helix. So when this is the tangent T, this is the normal N, and let's say this is our binormal. So the plane is going to change when we go along this helix. So here the binormal's position has changed. Here, this is the binormal position has changed, and here it has changed. So the torsion is going to have a value or magnitude that we can calculate. And I will show you how to calculate torsion kappa, which is curvature, how to find the unit tangent vector, how to find the principal unit normal vector, and how to find the binormal and acceleration vectors. And I showed you this graph to show you that also, for instance, for this point where the tangent vector is changing very rapidly, we are going to have a small circle, and then the normal vector is going to be pointing to the center of the circle. But if you're here at this point, the unit tangent vector is not changing that rapidly, so we are going to have a bigger circle to hug that arc length. And the normal vector is going to point to the center of this circle. And kappa here, which is the curvature, is a smaller than kappa here. Kappa for this little circle is bigger. So these are the ideas, and I am going to continue and explain to you the formulas and give you the formulas for these topics that we covered, and then I will do examples. So I have created a road here. Suppose the car is moving on this road, the curvature. The curvature here from A to B or from D to E is going to be very small, but the curvature from B to C or C to D, the curvature for these paths, B to C and C to D, is going to be larger. So here is going to have bigger curvature, but we are going to have a smaller curvature here because the road here is flat. Then again, another definition for the curvature here is the rate at which the unit tangent vector t changes direction with respect to arc length is called the curvature. So that's another definition for the curvature. The curvature of a point is 1 over the radius of the circle that is hugging the curve at that point, or the arc length. If the curve is flat, we need a bigger circle to hug the curve, so curvature is smaller. If the curve is bent, we need a smaller circle to hug the curve, so the curvature is bigger. The notation for the curvature is kappa, K, and this is, curvature is going to have multiple formulas. There are 3 formulas. That's one formula, 1 over r, radius of the circle. Another one is the magnitude of the change of the tangent vector with respect to arc length. And this is the formula for the unit tangent vector. If, again, as I told you earlier, when we define r of t is the vector function of a smooth curve or path, then we find r prime for r. We divide it by r prime, magnitude of r prime of t, to find the unit tangent vector. So to find a unit vector, we always divide the vector by its magnitude. So if I divide r prime by its magnitude, then I have a unit tangent vector. But r prime by itself, without this division here, is going to give me a tangent vector. To find the unit tangent vector, I have to divide it by its magnitude. And then the changes of the unit tangent vector with respect to arc length, that is, the magnitude of that is going to be called kappa, or the curvature. Then another formula for the curvature is, if we find t prime with respect to t, that is dt divided by dt, not ds anymore, the magnitude of that, and the magnitude of r prime, which is dr, changes of r with respect to t again, the magnitude of that. So if I divide these two magnitudes, I also get kappa. There is a third formula for curvature that, let me just show it to you right now. It comes on the next section, is right here. I'm just going to go back and write it. So the third formula, kappa, is equal to V cross product of A divided by magnitude of V cubed. V is R prime, A is R double prime. So if we take the magnitude of the cross product of R prime and R double prime divided by the magnitude of R prime cubed, that gives us curvature. So there are four formulas. One formula here, another one here, another one here, and another one here. And they all give the same value. Depends on what we have or which one is easier to use for a particular problem. Now, if we want to find the principal unit normal vector, this is a definition at a point on a smooth curve described by a vector function RT. The principal unit normal vector for a smooth curve in the plane is n is equal to 1 over kappa, which is the curvature, times dt ds. So it's going to give us a vector, because dt ds, derivative of tangent with respect to arc length, is going to produce a vector. We are not taking its magnitude. The magnitude gives us a number, but tangent vector's derivative gives us another vector. Then we multiply it by 1 over kappa. 1 over kappa is just a scalar. So n is orthogonal to the unit tangent vector t, and n points in the direction in which the curve is turning. And that's another definition for the principal unit normal vector. And then there is another formula for it again. In this case, if we don't want to deal with ds, we could find dt divided by dt, and then divided by dt divided by the dt magnitude. So derivative of t over its magnitude. Anything divided by its magnitude turns it into a unit vector. So if we find the derivative of the tangent vector with respect to t, then divided by its magnitude, we will get the normal vector n. The binormal vector is the third unit vector defined by the cross product of the two vectors t and n. That gives us the b. And all these can be considered. T is a vector function, n is a vector function of t, and b is a vector function of t. And the three vectors, the binormal, the unit tangent, and the unit normal vector, are orthogonal vectors. They're all orthogonal to each other. So they're called the moving trihedral. And they also form three planes. So let me just leave some room here and show you a graph. So this is the B vector, this is our N vector, this is our T vector. As you see, it looks like the corner of the room or a right-handed rule. B is the same as z-axis. The tangent, the unit tangent vector looks like the x-axis, and N looks like the y-axis. So right now we have a plane here, which is the xy plane or the Tn plane. It is called the osculating plane. So this is our osculating plane. And then the plane, the wall that is across from you, or the plane that is made out of with B and N, or z-axis and y-axis, we call that one the normal plane. And then the other plane that is formed here, that is called the rectifying plane, which is the same as ZX plane or BT plane. So this is very similar to the movable right-handed rule coordinate system. The only thing is we are going to create these three when we move along a curve. So these three are located here at this point, and then here. So that's why they're called the movable right-handed rule coordinate system. And with those, we can determine torsion, acceleration, and everything for every given point on the curve. So before I go over acceleration and torsion, I would like to do an example, or a couple of examples. One is find the curvature of a circle of radius A. So to find the curvature, I need to find the unit tangent vector t, which is equal to r prime of t divided by magnitude of r prime. So first I have to find r. Since we have a circle with the radius of a, then r of t can be expressed as the radius. If it's a, then we put an a. If this a is 9, then we put a 9 here. But it is a, so we get a cosine of ti plus a sine of tj. That is how we can, this is the equation or the vector function of a circle. We are going to pick different t's. When we pick different t's on the xy plane, then we are just going to get all these points. We get this vector, we get this vector, we get this vector, we get this vector. And if we trace all these points, we will get a circle with a radius of a. So this radius here is a. So that's what this is going to produce. It's going to produce all these vectors that when they're traced forms a circle. Now, in order for me to find the unit tangent vector, I have to find r prime of t, which is a negative sine. So this becomes minus a sine of ti plus a cosine of tj. Derivative of sine is cosine. Derivative of cosine is negative sine. That is why we have, that is why we have, just wanted to erase this here to be able to put a equal sign. So we get minus a. sine of t, because derivative of cosine is negative sine. And then we find its magnitude. And the magnitude is, we take that component squared plus that component squared. So we get minus a squared is going to be positive a squared sine squared. And then we square this one, a squared cosine squared. If I factor a squared from under the radical from these two terms, this is what I will get. And sine squared plus cosine squared is equal to 1. A squared times 1 is just going to be a squared, which is a. So that's the magnitude of r prime of t. Then to find the unit tangent vector, I take that and divide it by a. So minus a sine of ti plus a cosine tj divided by its magnitude a. So if I break this fraction into two fractions, I get minus a sine of t over a, and a's cancel each other here and cancel each other here. So I get minus sine ti plus cosine tj. So that is our unit tangent vector. Why did I need that? Because in order to find kappa or curvature, one of the formulas for curvature is that. Is going to be derivative of tangent vector and then divided by the magnitude of r prime. So I am going to, for this example, I am going to find derivative of that, t prime of t. So this is equal to t prime of t's magnitude divided by r prime of t's magnitude. So what is t prime? Derivative of sine is just cosine. Derivative of cosine is negative sine. What is the magnitude of t prime? It's just going to be that squared, which is going to be positive. When I square negative cosine t, I get positive cosine squared. When I square negative sine, I get positive sine squared. And when I add the two, I just get 1. So this is going to be 1 on the top. I have the magnitude of r prime of t. This is the magnitude of r prime of t here, which is a. So I get kappa is equal to 1 over a, which is a number, which is a scalar. So if the radius here is equal to 3, then this is going to be 1/3. If the radius is equal to 2, then this is going to be 1/2. Which makes sense because if you remember, I told you the formula for kappa is 1 over r. So if radius is equal to a, then kappa is 1 over a, which are the same values. So that's that example. Let's look at another example here. For this example, we are going to find t, the unit tangent vector, the principal unit normal vector, the binormal vector, and curvature again. So to find any of these vectors or scalars, we need to find the unit tangent vector. To find the unit tangent vector, we have to find r prime. So let me find r prime of t. R prime is minus 2 sine of t, I, because derivative of cosine is negative sine. Derivative of sine is just positive cosine, so we get positive 2 cosine of tj. Derivative of 3t is just 3k. We find r prime's magnitude, which is the square root of the components, the sum of the components square. So minus 2 sine of t squared gives me 4 sine squared of t. Then I have to square this one. That gives me 4 cosine squared of t. Then I square this one, I get 9. Again, if I factor a 4 from these two, I get sine squared plus cosine squared is equal to 1. 4 times 1 is 4. So I get square root of 4 plus 9, which is the square root of 13. So that's the magnitude of the velocity if this is a position vector. Or if this is just a smooth curve and this is its derivative, this is the magnitude of the derivative. Now I want to find t, and t is equal to r prime of t. And I have to divide this vector by a square root of 13, but when I divide this entire thing by square root of 13, I can break the fraction, and this one is going to have a square root of 13, and this one is going to have a square root of 13, and this term is going to have a square root of 13. So you're putting this thing here divided by square root of 13 to find the unit tangent vector. That's what I'm doing. So when I divide the entire thing by its magnitude, then I can write it like that. Then in order to find the normal, I need to find the normal's formula is t prime of t. So I have to find derivative of r prime, rather derivative of the t prime, t, and then divide it by its magnitude. Dividing it by the magnitude turns it into a unit vector. So to find the normal vector, you have to find derivative of that. So t prime is equal to derivative of sine is cosine. Derivative of cosine is negative sine. So this will become negative. Derivative of a number is 0, so we don't have the k term anymore. Then let me find its magnitude. I have to square that, and I have to square that. The square root of minus 2 is 4. A square of a square root of 13 is just 13. And then I get cosine squared. The same thing happened here. Minus 2 squared is 4. The square of a square root of 13 is 13. And then I get sine square of t. If I factor 4 over 13 from both of them, I get sine squared plus cosine squared, which is 1. So I get magnitude of t prime is equal to a square root of 4 over 13, which is a square root of 4 is 2, a square root of 13. Now I just have to find the n. I have to divide t prime by its magnitude. So when I divide this by its magnitude, this gets divided by this component and that component. So they cancel each other. 2 square root of 13 cancel this one and this one. I get cosine of ti minus sine tj. So that is our unit or the principal unit normal vector. Next, I'm going to find the binormal. To find the binormal, we are taking the cross product of t and n. So to find the binormal vector, we are going to take the cross product of tangent and the normal vectors. So this is equal to I think I need a little bit more room. Let me just write the I is going to have the tangent vector is minus 2 over square root of 13 sine of t, that is the I component. The I component for normal is minus cosine of t. For the j component, this is the j component of the tangent vector, 2 over square root of 13 cosine of t, and this is the j component of the normal, which is minus sine t. And then the k component, this is the k component for tangent. And here is 0. To calculate a determinant, I have to put I, that's one way. I mean, there are multiple ways, but this is one of the way to calculate a determinant, is to put the I and j columns, the first and second columns, outside. And then I'm going to multiply these guys, get 0. I multiply these guys, I get plus 3 square root of 13 times negative cosine. It makes this negative cosine t of j. I multiply these 3, that's what I get. And then I multiply these 3. Negative times negative is positive. Sine times sine is sine squared. And then I have the k. Then I also have to multiply this diagonal here. That's 0, because I have a 0 here. 0 times anything is 0. Then I multiply these 3. I get minus 3 square root of 13 sine of t I. Then I multiply these. Negative times positive is negative cosine squared. Let me just write the coefficient first. The coefficient is that. And then I have the cosine squared. And then I have a k. And then to calculate the determinant, I go further. I take these guys, minus 3 square root of 13 cosine of tj plus 2 the square root of 13 sine squared of k minus these guys. But when I subtract these, this negative will change this sign to a positive. This negative changes the sign to positives because I have these guys minus these guys. But that negative negates these two and they become positive. 3 over square root of 13 sine t of I plus 2 square root of 13 cosine square root 2 of k. This is a k component and this is a k component, so I can add these two. If I factor 2 square root of 13 and a k from both of them, they're like terms, sort of. So I factored that and I factored the k. Then I get sine squared plus cosine squared, that's 1. So I'm left with 2 over square root of 13k. And then I have this one and I have this one. So I have an I component, which is 2 or 3, the square root of 13 sine ti minus this 3 square root of 13 cosine tj. And this is the binormal vector. So that's another vector function of t. So once I have the 3 of them, now I just have to find the curvature kappa. And for kappa, I could use the magnitude of t prime, because I found t prime somewhere and I have its magnitude. So the formula for this one is the magnitude over the magnitude of r prime. And I have both of them. The magnitude of T prime is 2 over square root of 13. The magnitude of R prime is a square root of 13. And to calculate this fraction, I can just go out in. So I get 1 times 2 is 2. The square root of 13 times the square root of 13, and that is the value of the curvature. So curvature is 2 over 13, which is a scalar. But if you notice, B is a vector function of T, N is a vector function of T, and T, the unit tangent vector, is also a function, a vector function of T. I will stop here for 13.4, and then I continue on the next lecture for 13.5.